Okay, for example one, as we kind of just started to talk in class today, more or less, we're going to go ahead and take some time to examine each graph and decide if the graph is a function. We're also going to take some time in part B to identify the function's domain. And then in part C, we're going to take some time to identify the function's range. If we look at part A, to see if that's a function or not, we would just quite simply run the vertical line test. And as I look at this particular discrete function, I notice that it would pass the vertical line test. Each input is mapped on to exactly one output. In part B, we're asked to identify the function's domain. And in this case, for some of you today, I talked about we could go for a walk. If you've already seen this example today, you could just fast forward a little bit. That's not a problem. We'll catch up in part 2 of this example. When you go for a walk, this is you. It'll make you dizzy. Whoa. When you go for a walk, to answer the question specifically, what is this function's domain, you start walking along the x-axis, because as we've discussed, domain is defined as possible values of x. And if you start at the negative x-axis, little side note, we always start smallest to largest, we would start at -2. And as I look up and down, I don't see any points there, so I'm going to move you over a little bit to -1. And that's you standing there at x equals -1. And if you're standing at x equals -1 and you look up and you look down, you don't see any points there. There's no points up here. There's no points down here. So -1 can't be in the domain of this particular function. However, if I fast forward a couple steps and I put you at x equals 1, and you just happen to look up a little bit, you can see that where x equals 1, there is a corresponding y value. And it's for that reason that we can start to understand that x equals 1, 1 is part of our domain. So with that, we're going to start writing out our domain. Because this graph is discrete, if you look back at your foldable, we actually have to list out all of the individual values of x. We're going to use set notation for this. So we would say D, our domain is, or D equals, x for when x is, and we're starting at 1. So we're going to start listing out our x values here. And then I continue my walk, and I'm walking along. And right now I'm at x equals 2, and I look up, and I'm like, oh, look, there's no y values there. So 2 can't be in my domain. 2.5, 2 3/4. Now I'm over at 3, and I look up, and I'm like, oh, look at that, there's a point there. So 3 would be in the domain of this function. I'm going to look for other possible values of x here. If I move over a little bit, 4, like got me right in the chest there. Didn't even have to look. And if I walk a little bit further, looking for, again, possible values of x, at 5, I see that there is no output there. There's no y value that corresponds to an x value of 5, so I can't list 5 in my domain. So I'll keep walking along the x-axis here. And lastly, I notice, hey, 6 is a possible value of x, So that would be the last value of the domain there. So the domain of this function is just 1, 3, 4, and 6. Next, we have to do our range. We do the same thing, except when we do work to identify the range, we now have to go ahead and take a look at possible values of y. So I'm going to have you take a walk along the y-axis this time. And we always start on the negative side because we write our range values from smallest to largest. Because this is a discrete graph, it's dots, I'm going to go ahead and use set notation once again to describe the domain of this function. So, I'm sorry, the range of this function. We're on the y-axis now. So right here, I'm standing at y equals -6. And as I look up and down, or depending on how you look at it, side to side, I don't see any values down here. So negative 6 can't be in the range of this particular function. And if I walk along, negative 5 also not in the range, negative 4 is not in the range, negative 3 is not in the range. But long last, when I stand here at negative 2 and I look down all the way over here, or to the right, depending on how you look at it, do you see how there's a point there? That means that the y value of negative 2 right here does have a corresponding x value. Negative 2 is indeed in the range for this function, so we can start writing our range. I'll do it in green. So here we could say R for range, and these are again y values. Remember, we defined the variable, and now we're going to describe it. And the first range value I have is negative 2. Then I'll continue my walk here. Walking along, I don't have any range values at 0 or at negative 1 that I can see. At positive 1, I don't see any dots. Oh, but at positive 2, I see a dot. So I see another range value there at positive 2. I don't see any at 3. I don't see any at 4. Oh, yeah. But I do see 2 range values. 2 values at 5. You only have to list it out one time. You don't have to write it twice. So this graph does have a range of 5 as well. And that's the last dot I see. You could keep going. You could walk all the way to positive infinity if you wanted to, way up here. But you wouldn't see any dots as you read across. So hopefully that helps you there. With part 2, you may notice that this graph is not discrete. It is indeed continuous. And when we have continuous functions, it's beneficial, I think, to use our interval notation. So I'm going to show you how to work that. First of all, I would do the vertical line test on this particular graph, and I noticed that this graph would pass the vertical line test. So indeed, yes, this is also a function. I'm going to go ahead and start identifying the domain of this function. And I'm going to have you take a walk again. And again, when we identify the domain of a function, we're looking for our possible values of x. So you'll see now I'm standing at negative 5. And that's kind of tough. If you look up a little bit, you don't necessarily immediately see a dot. So for the sake of teaching you something new, I'm going to go ahead and move you over for just a second. I'm going to put you at x equals negative 2. Now, if you look up when you're standing at negative 2, you will see a dot. It'll be right there. See that? There's an output value that corresponds to an x value of negative 2. Now, if I go ahead and I move you back to negative 5, you'd have to use your imagination a little bit. But this graph, being a parabola, I'm not sure if you remember that or not, would go up and out forever and ever and ever. So we'd have to use our imagination a little bit. If you look up, eventually, indeed, you would see a dot. So there is an output for an x value of negative 5. It's just hard right now to see what that is. Furthermore, if I slid you all the way down, maybe even to say, hey, you know, x equals negative 10 or x equals negative 20, and you could use your imagination to see where this parabola were going, it wouldn't matter where I put you on this negative x-axis. You would see an output eventually when you look up. For that reason, we can say that this graph for the domain goes all the way to negative infinity. It's defined the whole way down. And I could have you walk all the way along this x-axis. And the same would be true, because there's symmetry in this graph, if I put you all the way over on the positive x-axis. Eventually, if you look up, there's going to be points there. And it wouldn't matter where I put you. This graph keeps going up and out forever and ever and ever. So you would see points no matter where you were standing on the positive x-axis. It's for this reason that we can say this graph goes to positive infinity. So when we see this parentheses, negative infinity, comma, positive infinity, you could come to understand that that graph is going to take up the entire x-axis for your domain. If you wanted to write this using set notation or algebraic notation, you definitely could. You might recall that this was our most common domain that we're going to run into. We say our domain would be x for when x is the set of all real numbers. But those two things are logically equivalent, and you can choose. If you prefer negative infinity to positive infinity, you could use that. But if you really do like the set notation and you just want to stick with one thing, you could use that also from your foldable. Now we have to talk range. So I'm going to do that in a slightly different color. Range, again, is possible values of y. So I'm going to go ahead and flip you over so that you can start walking along the y-axis. When we walk along the y-axis, you see if I'm standing down here at -4, I don't see any values. I don't see any at -3 or -2 or -1 or 0 or up to 1. I don't see any until I get to 2. But then after that, oh buddy, check it out. After y equals 2, I see values no matter where I stand on that graph. Simply put, this graph goes from 2 up. So how do we write that? That's always the tough part. You can kind of all see, I think, at this juncture, that this graph goes from 2 all the way up. So with that, keeps going and going and going. You can see that, it starts at 2 and goes all the way up. The tricky part is then how to write that. Well, because this graph is defined at 2, we put a bracket at 2, and then it heads towards positive infinity. If you wanted to write that in set notation, how is that going to look? Well, we wouldn't write d, and we wouldn't write x, because this is range. So if I wanted to do the range, make this red for you, I would quite simply say that my range, give myself a little space here, my range would be my y values, because this is the y-axis, for when y is greater than or equal to positive 2. And that's it, because my values start at 2 and go up. And you could use whichever you like. You could use the set notation, or you could use the interval notation. Let's do a couple more. In part 3 here, you'll see that first graph, when you go ahead and run your vertical line test, it fails miserably. So it's in that way that this graph is not a function. There are multiple inputs that are paired onto more than one output, and that definitely violates our definition for a function. If I want to understand what the domain of this graph is, however, because relations can have domain and range regardless of if they're functions or not, we could take this little guy here and we can make him walk along the x-axis. And what I see is that if I'm standing at -2 and I look up or down, I don't see any values. If I stand at -1 and I look up or down, I don't see any values. But at long last, when I stand at x equals 0, I start to see a point for this particular curve. See that there? That's where this graph is defined. So I see my first value at 0, and then lucky me, as I keep walking, no matter where I stand after x equals 0, I see outputs that come back out. You could write this in one of two ways. We could say that the graph starts at 0 and heads towards positive infinity with a parentheses, or we could use our set notation, where our domain is the set of all x values for when x is greater than or equal to 0. J-Leno bracket. Now, you might be sitting there in your house right now or wherever you're watching this and saying, well, why is Mrs. Lucas using brackets for when I have a number, and then maybe parentheses for these infinity values? And it does go back to our foldable, so I was just going to show you where you can kind of take a look at that a little more closely if you were concerned. You might recall that that's this piece right here. Parentheses are used when your point is not in the domain or range. So if you see an open circle on your graph, or positive infinity or negative infinity, you're always going to put parentheses around those because those are points that are not included in your domain or your range. You can't include positive infinity in your domain or your range. Like, I don't even know what positive infinity is. It's just like way, way out there. So we can't bracket that in. It's not, we approach it, but we don't actually get there. And that's kind of another way you can think about it. Brackets are reserved for when you actually get there. So if you can draw a point and that value is contained in the domain and the range, you use brackets. So just to kind of go back to how this notation got used, do you see how 0, 0 was a point? So I could use brackets right there. However, this graph heads out towards positive infinity. That's only something I approach. So I had to put parentheses right there. Okay, whoops, random smiley. Okay, now we got to do our range. So we'll go ahead and I'll do this in blue. Imagine you're standing here on your y-axis and you're standing at -3. This graph not only goes out in this way, but it also kind of grows to continue on, you know, if you use your imagination. This graph kind of continues on and on and on forever and ever. So both vertically from top to bottom. So as you're walking along, it's kind of hard. You got to use your imagination again a little bit. If I'm standing at -4 right now, it looks like there's no points there. But if you could predict where this graph is going to go, you could see that eventually, I'm going to invade some space here. Eventually, if I follow the trend of this curve here, I would get values that come down to -4. They're just not readily seen on the graph that we have displayed here. So if I use my imagination a little bit, I see that range values of -4 do exist. Same for -3 and -2 and -1 and 0 and 1 and 2 and 3 and 4. This graph would go on and on and on for all values of y. And it's for that reason that we can say our range goes from -infinity to positive infinity. If you were writing this with your set notation, we would say our range values are y values, where y is the set of all real numbers. And you could use either or. And then graph number 4 here. If you are walking along, let's steal you from right here, starting on your negative x-axis, again, we always start smallest to largest. Right now I'm thinking, is it a function, you know? Would it pass the vertical line test? And as I look at it, the answer to that question is yes. Every output is paired, or every input, rather, is paired with exactly one output. So that does meet our definition for a function. And then as you're kind of rolling along, -2, I don't see any domain values, and -1, I don't see any domain values, but I do start to see them right at 0 there. And then from 0 on, I see them. Do you see how 0 gets included in our domain? And then I walk towards positive infinity. So if I use my interval notation, it starts at 0 and heads towards positive infinity. Now, we could also use our set notation. We could say that our domain is values of x for which x is greater than or equal to 0, because we go from 0 on. The range values, if you take a look, this particular function, I'm at -4, -3, -2. I don't see anything. On this screenshot, it doesn't show up all that well, but I do have a point there at 0, 0. So that's going to be the first range value that I see also. And then this graph goes up and up and up forever and ever and ever. It's not ever going to stop increasing. So it goes all the way up is where it's sort of behaving, if you will. So it goes from 0 to positive infinity there also. So I can write that in the same way. And then if I wanted to write that in set notation, I would just say my range values are my y values, where y is greater than or equal to 0. Close my bracket out there. All right, next one here, part 5. If you ran the vertical line test on that, I know it looks strange. It looks a little dodgy right in here, but there's no points there. So even if you drew that vertical line at -1, that line isn't going to pass through any points on our graph. I know that the graph looks like it gets vertical, but it only actually gets really, really close to that -1 line. It doesn't actually touch it. So this graph can be deceiving. This would pass the vertical line test. So this is a function. And what I see, this is interesting, I actually see 2 pieces to the graph. Do you? I see a piece here, and then I see a piece here. So it's in this regard that I could actually write my domain values for each of those 2 chunks, kind of separately. We talked about a little symbol today that is going to help us out a bit on this one. And that symbol was, let's see if I can find it for you. Oh, there it is. That symbol right here is the symbol for in union with. And whenever you have big chunks to your graph, we're going to go ahead and use that in union with symbol. So with that, let's talk about our domain. If you're walking along the x-axis, start on the negative side, and it doesn't matter where I put you. I can put you over here. You're eventually going to see pieces of that graph in negative infinity. But then, like I said before, there was this line, this vertical line at x equals -1. When you get really, really close to that line, you're like, ah, and you fall down a cliff. Ah, no, not really. If you're walking along that negative x-axis, you can get really, really close to -1, but you really can't touch it. So how do you write that with respect to your domain? Well, the domain for this yellow piece of the graph would just be from negative infinity to, oh, be careful, watch out. We go from negative infinity to -1. But -1 doesn't get included in the domain of the function. So I have to put a parentheses because I get really close to -1, but there's no point there. This will be in union with the green part of my graph, which picks up a little bit after -1. So if I look up, I see some points here. And then if I keep walking, I see points, I see points, I see points, all the way out towards positive infinity there. We would start again at 1 and head towards positive infinity. So that's that domain value there. I usually just do hyperbolas or these like graphs that have chunks to them. I usually just do interval notation. You definitely could do set notation with these, but I feel like that's a little more complicated. We could actually talk about what the set notation would be as perhaps a warm-up when you get back to class tomorrow. The range also has a little hiccup in it. We would need to write a range for the yellow graph and then a range for the green graph. But you'll see there's a little hiccup. We get really, really close to that line y equals 0, but we don't quite touch it. So when you walk along the y-axis, you're going to see way down here that there are points to your graph. But if you stood right on 0 right there and you looked up or down, you wouldn't see anything. It's like a big hole. But then after 0, you would, whoa, sorry about that. After 0, you would start to see some points again. So if you're walking along here, see how there's green pieces to my graph there? So it's in this way that we would write our range, a little bit like this. It goes from negative infinity to 0 and takes a break. Gets really, really close to 0, but doesn't actually touch it. So I had to put parentheses there. And then that's in union with 0 to positive infinity. And then number 6 there. I'm going to have you go ahead and type that one into your calculator. I'm going to have you try this one on your own, and we're going to talk about it together as a class tomorrow. So how are you going to get a graph? You're going to press your y equals button in your calculator. You're going to do second square root, and it was x plus 2 underneath that radical. So if you press graph. I want you to go ahead and give me the domain and the range of this particular function. And this will be where we pick up tomorrow. If you're not a fan of the approach I used in this video, I'm actually going to show you a little more concrete way to take a look at it tomorrow, because tomorrow we have like a hands-on sort of manipulative type activity to go ahead and take advantage of. But right now, as your concluding problem, you're going to take some time to tell me if this is a function and then write its domain and range. And that's where we'll pick up tomorrow. Have a nice day.